lecture 14. So currently we are doing the chapter 3. In the chapter 3, the second part of the chapter 3 is about analysis of beams. So in the analysis of the beams, we started with Euler-Bernoulli beam, that is plane sections remains plane and perpendicular even after the deformations. So based on that and based on the statics, we have derived that m by ei is equals to 1 by rho is equals to d square y by dx square, or this we might have called it as r, where r is the radius of curvature. Okay, and we also showed that dm by dx is equals to v of x, where m is bending moment, v is shear force, y is elastic curve, that is the deformation of the neutral axis, r is the radius of curvature, radius of the segment which bends like an arc. Okay, and this is also equals to 1 over kappa, where kappa is the radius of curvature. So, and further, dv by dx is equals to minus w of x. That is, if you have v, this is v plus dv, this is m, this is m plus dm, the loading is w of x, this length is dx. So in that case, based on the equilibrium, the above things are derived, where w is the distributed load on the beam. This is a beam structure, so with Young's modulus E and cross-sectional inertia IE. So based on the equilibrium, we might have showed this one, and using all these things, we further showed that d square dx square ei d square y by dx 2 is minus, when beam is homogeneous, that is E of x is E naught, which is a constant, and if beam is prismatic, that is the cross section remains same, then I of x is equals to I naught, or both are constants. This is one constant and this is a constant. Then we can take these two EIs outside and we can write EI d4 y by dx 4 plus w of x is equals to 0. this was our governing differential equation in the strong form for the beam. Or ordinary differential form for beam. But we know that we are not solving this problem, and we try to solve this problem in an analytical manner for one of the case in the previous lecture. So we have already solved this thing in the previous lecture, and we also showed an analytical example how to solve over these things and the requirements of an exact solution for or the differential form using a method of weighted residual in the previous class, and came up to the weak form or the integral form of the Euler-Bernoulli beam. The weak form or the weak form or the integral form can be written as so what we did was, when we substitute our y is exact solution, but we know that we are only seeking for y tilde, then there exists an error. Okay, so when we substitute, instead of y, we substitute this, then we'll end up with a residue in this equation. So what we'll get is r of x is equals to ei d4 y tilde by dx4 plus w of x. So and we take V 0 to L, the length of the beam. The R of X in this case is EI d square y tilde by d4 W of X dx is equals to 0. So I will rewrite this as the first term, which is 0 to L V E I d4 dx4 dx plus integral 0 to L V of X into W of X dx is equals to 0. This is distributed load. Okay, we'll come to that at a later point as we progress further. Next, what we do is we take this first term and apply integration by parts. If we apply integration by parts, we can write it. The integration by parts can be taken as integral V du is equals to uv minus of u dv. This is the integration by parts. By applying this, so here this is v, I consider this one as du, then I can rewrite the first term as integral of, first we have to write the boundary term, which is v times ei d cube y by dx cube 0 to L minus of dv by dx ei y by dx cube. Dx is the first term and the second term remains as it is, so it is 0 to L further. What I do is apply integration by parts again, then we'll have minus of dv by dx ei d square y by dx square plus d square v by dx2 ei d square y by dx square dx plus 0 to L vw dx is equals to 0. Now these two are called boundary terms, and the boundary terms define our boundary conditions. So for example, we know that E I dm by dx, which is nothing but EI let me write it as V EI V is the shear force, can also be written as EI d cube y by dx cube is the shear force. This is the shear force, or EI m is equals to EI d square y by dx square. This is bending moment. So either you can mention this quantity, that is bending moment times EI, or you can mention EI times the shear force, or EI into this as the boundary conditions. So anyway, what are the boundary conditions for a beam? So either if you consider a beam, you can mention y, you can mention dy by dx, you can mention d square y by dx square, you can mention d cube y by dx cube. So y is nothing but your transverse displacement, transverse deformation or displacement, and this is nothing but theta, which is equals to slope of the elastic curve. And if I multiply EI, we have just seen that it is equals to bending moment. If I multiply EI to it, which is the material constants for a given selected beam, this is your shear force. So either you can mention a displacement or slope or a bending moment or the shear force for a given beam. So that means you can, since this is a fourth order differential equation, if you mention y or dy by dx, these are called kinematic boundary conditions. If you mention m or v, it is called natural or force boundary conditions. Okay, further you need to understand that these boundary terms should vanish when your kinematic boundary conditions are mentioned. So in order for the kinematic boundary conditions are mentioned, because in this you will only see the presence of natural boundary conditions, because if this is mentioned, this can stay as it is not a problem. Similarly, when B is mentioned, which is nothing but shear force is mentioned, this can stay as it is. However, if you mention kinematic boundary conditions which nowhere appear in this equation, you want those terms to vanish. That can only happen when a y or, that is when kinematic boundary conditions are specified, their corresponding virtual components should vanish. That means, that is, if y of x naught is equals to delta, that implies at the same place your virtual x naught should go to 0. Similarly, but kinematic boundary conditions are of two variants, that is dy by dx at x1 is equals to alpha, that implies dv by dx at x1 . vanish means 0. They should be zeros. So whenever these are mentioned, if these takes 0, the advantage what we get in the weak form is these things will go to 0 when kinematic boundary conditions are specified. Same, this fellow also would vanish when kinematic boundary conditions are specified. In that case, we are only left with these things. So the advantage what we get is, when I rewrite this statement again, so V ei d cube y by dx cube 0 to L minus dv by dx ei d square y by dx square 0 to L plus 0 to L d square v by dx square ei t square y by dx square. At this point, I don't have to put an approximation. I'm sorry about it. You don't have to put an approximation as it is at this point of time. Even if it is an approximation, at the boundary, the y tilde and y has to match each other. So in any case, that y tilde should not be there. So dx plus vw dx is equals to 0. Somehow we will see that this statement, we will somehow write it, not now, somehow would give stiffness contribution, this term, and this term will give distributed forces, and these two terms has two cases. When it is kinematic boundary conditions, they vanish. If it is natural boundary condition, they give contributions from point loads or moments, or I will say point generalized forces, point generalized forces. When I say generalized forces, both the P as well as M are called as generalized force. This is force, this is movement, but when I call generalized forces, I can call both of them as generalized forces. Similarly, my generalized, for example, generalized degree of freedom is nothing but your y and dy by dx both, because this is its conjugate and this one is its own conjugate. So if this becomes generalized, this set becomes generalized forces, this set becomes generalized degrees of freedom. So that means this is, again, let's come back to the original thing, why I have written this. So this fellow will give us something like some k times d, and this fellow will give let me put it in the other side, will give contribution due to the forces. This is distributed forces, and this term will come and give you, this fellow will also contribute and come and give point loads. So the contribution would be such that this will give you forces as distributed, forces as loads, and that will give point loads, and Kd is equals to F will be as it is remained for the things. And kinematic boundary conditions doesn't appear in such kind of a set. That's the reason the purpose of taking these things is such that the kinematic boundary condition doesn't appear. But this statement together with this integral form, if this integral has to be less than infinity, that means it should belong to H2. And if it has to satisfy this condition, further it says that it has to be H2 0. So our virtual displacement V should belongs to Hilbert space 2 with a homogeneous conditions. So that means wherever U is mentioned, wherever Y is mentioned, and wherever the generalized degrees of freedoms are mentioned, there corresponding generalized virtual degrees of freedom should vanish. That is called H2 0. So this weight is not an arbitrary weight where you can take whatever you want, but there is only a certain set of functions can only be used such that we can write it in this integral form. Okay, so but how to choose the V, I'll come to it at a later point. We'll use Galerkin methods. That means somehow we will come to know that our choice of V would follow very similar to the shape functions form, which I'll come to it later. So before that, I would like to again stop here. This is the review of the previous things. This is also called as weak form of the beam. This we will get it onto the discrete form at a later point after doing certain simplifications, and for that we also have to take some approximation. But this is to develop this thing, we need this form, this weak. This is the integral form, or the weak form is necessary. Weak form of the beam. Okay, so let us see a certain example of how to develop a beam element first, and then I will go back and connect it with this virtual form of the beam, and we will gel it and try to cook up our stiffness matrix in two different ways. Okay, so for that, before I change topic at this point of time, I would like to stop and see if there are any questions from the gallery. For example, without any distributed load, then in that case it is EI d4y by dx4 is equals to 0, and this is my given beam element. It has at every node 2 degrees of freedom. One is the transverse displacement and the transverse slope, whereas for a noded two-noded bar element, we have axial degrees of freedom, that is along the x direction. Here we have y direction as well as the slope. So that's how a bar element is different from the beam element. For example, here when I consider a two-noded thing, we have 4 degrees of freedom. That is the displacement along the y direction at the first node, the slope at the first node, the displacement in the y direction at the second node, the slope at the y node. So these are 4 degrees of freedom. That is d1y, theta 1y, d2y, and theta 2y. So we have 4 degrees of freedom for a two-noded beam. So when I integrate this EI d4y by dx4, I would get something of, this is my general solution for that. Now what I am doing in this exercise is I am trying to find out my unknown coefficients A1, A2, A3 and A4. Those things are using the boundary conditions that is available for me. The boundary conditions that are available from me is at x is equals to 0, I know my y. At x is equals to L, I have third boundary condition, which is y is equals to d to y, and the slope is equals to theta to y. So if this is my equation of the displacement, general solution for the displacement, my slope would be of dy by dx, that is equals to 3a1 x square plus 2a2 x2 plus a3. So using this boundary condition 1, 2, 3, 4, I am determining my all the 4 unknown coefficients. The unknown coefficients from the BC boundary condition 1 appears to be my theta 4 is equals to d1y, and from the BC2 boundary condition 2, I determine that my A3 is equals to theta 1y. Now the later part is to determine my another coefficients, which is y of x is a1 x cube plus a2 x square. Now I need to determine these two knowing the boundary condition 3 and 4. When I substitute boundary condition 3, that is at x is equals to L, this value goes to d to y. This is a1 L cube plus a2 L square, theta 1 yl plus d delta 1 y, which is equation 1. And the boundary condition 4 says that the slope at x is equals to L is given by theta 2 y, that is 3 a1 L square plus 2a2 L plus theta 1 y is the equation 2. So in order to obtain my a1, what I did is I took this equation, multiplied an L and subtracted 2 times of this equation. So I end up getting my a1 as something of this form. Similarly, now since I already know a1, I need to determine a2, where I am currently working out. So we'll continue from here. So if you have missed anything, please let me know, or if you want me to repeat anything, please let me know. Meanwhile, I'll try to obtain this a2. So a2 can be obtained as a1 L cube minus theta 1 L plus minus delta 1 y plus d2 y. But we already know our a1 is determined as one by L square L minus L theta 2y plus d2y minus L theta 1y plus 2 d1y minus d1y plus d2y. So this will determine our a2 as 1 over L square minus L theta 1y minus L theta 2y plus d1y minus 2 times of plus of 2 times of d2y. So that's how I determined my L1, L2, sorry, A1, A2, A3 and A4. Since I know now all the coefficients, I can rewrite my equations as something like this. So my y is equals to y of x is equals to, for simplicity what I will do, I will write my d1y as simply redefine as d1, theta 1y I simply define as theta 1, because carrying over 2 subscript is really painful. And similarly, d2y, I define it as d2, and theta 2y, I simply define it as t2 for brevity. So I can rewrite this one as a1 x cube plus a2 x square plus a3. So anyway, we determined a3, a4 as theta 1 x plus d1. Okay, since I'm resubstituting these things in this manner, this is my y of x, and since I know my a1 and a2, also now I can rewrite this fellow as my a1 was given by L theta 2 minus d2 minus L theta 1 plus 2d1 x cube by L cube plus a2 is given by minus L theta 1 minus L theta 2 plus d1 minus plus 2 d2 x square by L square plus theta 1 x plus d1. So this is my y of x. So even though it is in this polynomial form, I want to rewrite this y of x by rearranging this term in such a manner that it is equals to some times of d1 plus something times theta 1 plus something times d2 plus something times theta 2. Why I would like to write it in that manner, I'll come to that in a short while. So we want to rearrange into below form. So if I try to rearrange into the below form, I can get something like this. Y of x is equals to, let me collect the terms. So it is 2, I will write 1 by L cube first, 2 x cube minus so anyway, I'll rewrite it for shortly. We can rearrange the terms later. Since I know the solution, I'll rewrite it plus L cube plus this is equals to d1 times. Similarly, this will become x cube minus 2l x square plus x L square into 1 by L square into theta 1 plus minus 1 by L cube minus 2x cube plus 3L x square d2 plus 1 over L square x cube minus L x square theta 1. So it is little bit tedious to kind of sort out the thing. Since I have already ready my solution, I have given it to you. You can sort it out in this manner at your free time. But this is the solution, you will get it. But what I am writing this is, it is of something of this form. This is n1 d1 plus n2 theta 1 plus n3 d2 plus n4 theta 2. So where n1 of x can be simply identified as 1 by L cube 2x cube minus 3x square L plus L cube, and n2 of x is identified as 1 over L square x cube minus 2L x square plus xl square, and n3 of x is defined as 1 over L cube minus 2 x cube plus 3L x square, and n4 of x can be defined as 1 over L square x cube minus Lx square. So if you identify this similar to what we have done for a bar, so aside for bar, we said that my u of x or u tilde of x is equals to u1 n1 plus u2 n2, or this is degree of freedom 1 n1 plus degree of freedom n2. So this is UINI form. If you see that these are also degrees of freedom. This is the first degree of freedom. This is second degree of freedom. This is the third degree of freedom. This is fourth degree of freedom. So if I rewrite it as my D1 as D1 and theta 1 as D2, D2 as capital D3, which are my generalized degrees of freedom, and theta 2 as my D4, I can write my y of x in this case as n1 d1 plus n2 d2 plus n3 d3 plus n4 d4, or simply summation ni di. I is equals to 1 to degrees of freedom for the given element. So, and n would be called, n's are your shape functions, and di are generalized degrees of freedom. So our n1, n2, n3, n4 are the shape functions for the given beam function. And there are certain characteristics associated with the shape functions of these things. So at this point of time, I will try to stop and just see if there are any questions from the gallery. On solving equation 1 and 2, we will get a1 and a2. You take that a1 and a2 and write it in certain form as y of x. We will get it in something of similar these things. Later what you want to do is, you don't want to write it as a1 of x cube, a2 of x square, theta 1 x d1, but you want to write as some polynomial times d1 by rearranging the terms as something times d1, something times theta 1, something times d2, and something times theta 2 by rearranging the coefficients. So what what we obtain is 1 by L cube 2x cube minus 3x square L plus L cube d1, 1 by L square x cube minus 2L x square plus xL square into theta 1, 1 by L cube minus 2x cube plus 3Lx square d2 plus 1 by L square x cube minus Lx square theta 1. This is what you will be obtaining it. If you look at it, when we write it in this form, I can again re-show that it is of this form: n1 d1 plus n2 theta 1, n3 d2 plus n4 theta 2. If I define my n1, n2, n3, n4 from the above definition as, by the above sorting out, as 1 by L cube 2x cube minus 3x square L plus L cube, and n2x is 1 by L square x cube minus 2L x square plus xL square, and n3 is 1 by L cube minus 2x cube plus 3L x square, and 4x is 1 by L square x cube minus Lx square. So if you look aside and look back on the previous topics like chapter 2, for bar we have noticed our approximation, we are writing it as u1 n1 plus u2 n2 because it is nothing but degree of freedom times its shape function plus degree of two its shape functions, sum of all degrees of freedom. So I define similarly my degree of freedom d1 as capital D1, which is generalized degree of freedom, and theta 1 as degree of freedom, generalized degree of freedom capital D2, and D2 as generalized degree of freedom capital D3, and theta 2 as generalized degree of freedom D4, then I can write my displacement, which I obtained it as n1 d1 plus n2 d2 plus n3 d3 and n4 d4, or summation of ni di I running from 1 to 4. And all the above definitions of n1, n2, n3, n4 are nothing but the shape functions, and di's are the generalized degrees of freedom. This is what I have derived in this class. But now let us look at certain characteristics of these shape functions. Firstly, these ni functions, these shape functions n1, n2, n3, n4 are called Hermite shape functions. For bar, these are not Hermite. For a bar element, this is for the beam. For a bar element, these are called Lagrange shape functions. But for beam, it is called Hermite shape functions. So that means the characteristics of these shape functions are little bit different compared to that of the bar. So let us see the characteristics of these shape functions. The characteristics of these shape functions are something like this. So firstly, for a beam element, you need to understand that N1 at x is equals to 0 is equals to 1, and 0 at all other nodes. Similarly, dn2 by dx at x is equals to 0 is equals to 0, and 0 at all other nodes. So that means there is certain characteristics. In a beam element, the column vector is not, if you remember in the bar element, the summation of ni's is equals to 0. The properties of the Lagrange shape function is, for Lagrange shape function, evaluated at any given point, x is equals to 1. However, this is not true for beam element. For the beam element, you can see that n1 plus n3 is equals to 1 and dn2 dx plus dn4 by dx is equals to 1. These are the two sets which are different from n1 plus n2 is equals to 1, or summation, or if you have 4 degrees of freedom in bar element, we would have written in the bar element as n1 plus n2 plus n3 plus n4 as equals to 1 if there are 4 degrees of freedom in a bar element. However, for the beam element, it is not true. And why it is only true for this order is because the shape functions, so if you look at it here, the shape, this corresponds to the shape function 1, this corresponds to the shape function 2, this corresponds to shape function 3, this corresponds to shape function 4. So these two are related to translational degree of freedom. However, these two represents rotational degrees of freedom. So that means not only our rigid body translation has to be represented by our shape functions, but also a rigid body rotation has also to be demonstrated by our given approximation. That is, our y of x should be capable to capture, if you take an approximation for a y of x, it should able to give you a rigid body translation, as well as if you differentiate it with respect to x once, then the dy by dx approximation what you made should also represent the rigid body rotation also. So that both the criterias will help you to obtain these set of two properties of the Hermite shape functions. One is the sum of n1 plus n3 is equals to 1, that represents all the rigid body displacements can be obtained through this given shape function or approximation. And similarly, dn2 by dx plus dn4 by dx is equals to 1, which represents all the rigid body rotation can also be obtained by the assumed y of x, which is nothing but, we assumed y of x as a1 x cube plus a2 x square plus a3x plus a4. Our assumed this approximation will capture not only translational rigid body motion, but also rotational rigid body motion. This is translation. Rigid body motion is rigid body translation, and the second one is rigid body rotation. Both the things can be obtained. This is rigid body translation, and this is a rigid body rotation. If these two properties are met, then our element can have these two characteristics. So if somebody gives you a shape functions of a two-noded bar element and such that the mapping is d1 theta 1 d2 theta 2, then the corresponding shape function should satisfy these properties. Otherwise it is not a complete polynomial and your error will be much more, because if a rigid body motions is not captured by your two-noded element, then your error would capture it. If error captures it, then it would converge very slowly. So in the benefit of these things, our polynomial should be such that chosen just like what we have chosen in the things, from the lower order to the higher order. So the basis here in this case is 1 x, or other way around, we were choosing as x cube, x square, x1 is our basis, and our coefficients in this case is a1, a2, a3, and a4 as your basis. And we are choosing these things from the lowest to the highest degree of the polynomial. So if you skip any of one of the thing, then that will be taken up by the error, and the error starts dictating in a bigger manner at a later point of time. So knowingly or unknowingly, we showed that if we take y tilde of x is equals to a1 x cube plus a2 x square plus a3x plus a4, our shape functions are given by these things, which are nothing but n1, n2, n3, and n4 as our shape functions for a linear beam element. And linear beam good properties such that it can capture both the rigid body translation and rigid body rotation, and hence it has a better convergence than the other same two noded elements that are available outside. Okay, so this is a better approximation. So this is one way of developing the Hermite shape functions. In different textbooks, you find it in different ways to obtain it. So only thing you need to remember that for a Lagrange shape functions, for Lagrange shape functions, only DOFs are, or translation DOF are present. If they are present, so when you are finding the roots of the polynomial, you know that anything that is a root, when you are developing shape functions, anything which is a root will be a multiplier. However, since at each point not only your displacement but its gradients are also going to zero, they have higher multiplicity, and hence they behave a little bit differently from that of the shape functions of the Lagrangian functions. So that is the key point of it. So with this, we'll now come back as this as our approximation. This is equals to y tilde of x is equals to ni di as our things, where di is nothing but d1 theta 1 d2 theta 2 as our degrees of freedom. Okay, and n1, n2, n3, n4 as our shape functions. Okay, so with this, we have developed a two-noded beam element and developed its shape functions. At this point, I would like to take a break and check if you have any questions. So develop the stiffness matrix for beam element. So let's take again this two-noded beam. So we have, which is d1 theta 1 as degrees of freedom. This is capital D1. This is capital D2. This is capital D3, which is nothing but D2, and capital D4, which is equals to theta 2. So this is the node 1, this is the node 2, and this is, let's say, an element 1, which has these properties. Correspondingly, let us say the force conjugates at each and every point is nothing but, let's call the force conjugate for this guy is, let's call it as F1, and this one is, the force conjugate is M1, the force conjugate, this one is F2, and this one as M2. So we have different kinds of force conjugates. So now what I want to do is very similar to the shape functions, to the stiffness matrix, what I have obtained in the previous kind of a class in for the case of trusses. What I will do is I will keep 1 degree of freedom active, and I keep all other things constant, or not constant, 0, and then I'll try to see what are the equilibrium forces that would develop at each and every node. So in order to sustain the given degree of freedom, then we will come up with our equilibrium forces, which would automatically form the corresponding column vector in the stiffness matrix. So before going that, since we have 4 degrees of freedom, our K is a 4 cross 4 matrix corresponding to D1, D2, D3, and D4. So how do you determine this vector? To determine this vector, you just give D1 and give all other DIs equals to 0 and find equilibrium forces. So I will demonstrate how to do it for this given things. The same can be repeated for the other things. So since we already know our V, our Y of X, which we demonstrated earlier as this we have demonstrated earlier. So what I will do is I will take dy by dx, which is nothing but my slope. The slope would become dn1 by dx d1 plus dn2 by dx d2 plus dn3 dx d3 plus dn4 dx d4. Correspondingly, my bending moment m is equals to ei times d square y by dx square, that will be EI into dn1 dx2 d1 plus d2n2 dx d2 plus d2 dx2 dn3 dx2 d3 plus d2 n4 dx2 d4. Similarly, my shear force V is equals to EI d cube y by dx cube is equals to EI d cube n1 dx cube d1 plus d2 n2, sorry, this is cube, dx cube d2 plus d cube n3 dx cube d3 plus d cube n4 dx cube d4. We have expression for the y, theta, m and v. Now what I want to do is d1 our case d1 not equals to 0, but my d2 equals to 0 equals to d3 equals to d4. All the other degrees of freedoms are 0. In that case, my shear force and bending moment would simply become, my m would in that case would simply become EI d square n1 by dx square d1, and my shear force would become EI d cube n by dx cube of the first one d1. So, but what is my n1? My n1 is defined as we have seen earlier, we have seen it is defined as 2x cube minus 3x square L plus L cube divided by L cube is our definition of these things. So I will make use of this and try to find out my bending moment and shear force. Then I can get something like this. So let me do that math for you. So dn1 x by dx is 1 by L cube six x square minus 6xl, and dn2 by dx2, sorry, d2 n1 by dx2 is equals to 1 by L cube 12x minus 6L, and d cube n1 by dx cube is equals to 1 by L cube into 12. So now we got all the things, ingredients that are required. So I can simply write this thing as EI by L cube 12x minus 6L into d1, and this is EI by L cube into 12 d1. So this is my shear force when only, now let me evaluate. So this is our, so the shear force at this, the bending moment at this, shear force at this place is my F1. The bending moment at this place is M1. The shear force at this place is F2, and the bending moment at this place is that. That is, this is x is equals to L, and this is x is equals to 0. So when I substitute in these cases, I will directly obtain my those things. So which I can write it as F1, M1, F2, M2 on substitution. I'm writing it in a vector form for certain reason. So when only D1 is present, okay, can be represented as this is 12. I will write EI by L cube outside, EI by L cube 12, and when I substitute at x is equals to 0, my M would get as minus 6L, and when I substitute this at again, it would be the same thing. So which would come out to be, but since the direction of it is opposite compared to the positive one, you'll get it as 12, and this one would be 6L. Things what we have followed in using this one is anything that gives anti-clockwise is positive moment, and anything in the clockwise is a negative moment, and shear forces are also such that, okay, the shear forces which are in this manner for a beam will cause, this one will give clockwise movements. So these clockwise movements are kind of negative, and the shear force that gives anti-clockwise will be taken as positive. So the same convention has been followed, and based on that we get these kind of things. So that means in order to displace this node with only degree of freedom 1 and all other things are 0, these amount of shear force and bending moment I need to be enforcing to keep it under the equilibrium forces. Similarly, I can evaluate by keeping D2 and all other things are 0, D3 and other things, then I can write my stiffness matrix in the following manner. So, which is the stiffness matrix, which are obtained by keeping different things constant at different times. So similarly, what so this is what is the stiffness matrix we are obtaining. So if I rewrite it, it is k times d is equals to f, where d is are my generalized degrees of freedom and f are my generalized force vectors. So to explain it further, so the generalized degrees of freedom are nothing but d1, d2, d3, d4, or you can also write it as d1 theta 1, d2 theta 2. Similarly, the generalized forces are nothing but f1, f2, f3, f4, or you can write it as simply the f1, m1, f2, m2. These are the shear forces and these are the bending moment. Okay, so this is how one can obtain the stiffness matrix for a beam in more physical manner. So what we'll do is we will try to repeat this thing little bit in the next class, how we have obtained the stiffness matrix. We'll try to solve few problems and let us understand how the solution for the beams are obtained, how the assembly and other things are done. And once these things are completed, I will try to show a MATLAB program, maybe in a couple of classes from now, how to solve this numerically using a MATLAB program. Okay, so at this point of time, I will break and ask for a few questions. To minus d1 times. So when I substitute at x is equals to 0, I'll get this one as minus 6l d1, but my convention is such that the sagging moments are kind of I think okay, so I should have represented in this manner. So the sagging moments are positive, and let me rewrite it. Maybe that is, so if you consider sagging moments as positive, so in this side and this side, so this will cause a sagging, so this as positive, and the hogging moments as negative, then whatever you obtained would, even though it is a negative sign, it would be opposite to that of the thing, so you have to take it as positive CL. So that's the reason the sign was flipped when I'm deriving, taking it in the force format. Okay, so that's the reason. So when we try to take it in this manner, so we'll take this one as positive here and this one as positive here, and at that given point in the clockwise manner, so which was given as minus 6L, but which would be, if I consider in the opposite sense, it would be in the positive 6L. That's the reason this has to be A12 has been taken as plus 6L. I hope that answers the question. Don't worry, I will try to come up with the proper explanation again in the next class. Before we start assuming things, I will try to show how the signing convention has been obtained. So I think there is some confusion in the nature how I have taken it. But don't worry, I will try to show that in the next thing in a smaller way, and then we'll continue further. Okay, so if you have any other questions, you can ask now.